Hello, and welcome back to sections 17.1 and 17.4. In this video, we'll be going over example 3. So example 3 is going to ask us to use equations of motion to solve for some reaction forces and the angular acceleration of a disk that is rotating about a pin. So I've drawn that over here. So this is our three-body diagram. We know that omega is 10 radians per second, and that is counterclockwise, so standard right-hand rule. We're trying to find OT, ON, and alpha. So this is point O at the top up here. So the normal direction is up, so you can determine that by looking at where your center of gravity will go. So your center of gravity would rotate this way, and so the inside radius curvature would point up. Tangential would point to the right, so I just moved those coordinate systems up to match what I would see at the center of gravity. And then alpha, I'm just going to assume that it's the same direction. If I get a negative number, then it just means it goes the other direction. So this is an equations of motion problem because I'm looking for acceleration. So let's write down the equations that we would need. There are four possible choices. We used to have sum of forces x, sum of forces y. And now we're going to add sum of moments. That's going to be our new set of equations. Because these problems are rotation only, we're not going to use xy coordinates. It's more convenient to use normal tangential coordinates. So the equations we write are going to be sum of forces in the tangential direction. So for this problem, that is to the right, equal to mass acceleration of the center of gravity in the tangential direction. Now this isn't terribly useful, so a lot of times what we do is we sub this out. So if you remember from previous chapters, we can rewrite the acceleration of gravity in the tangential direction using alpha. So that becomes mass times r alpha. So I'm going to give this a subscript g. So this is the radius from the rotation point, so wherever it rotates, in this case O, to that center of gravity. So distance between rotation point and center of gravity. All right. We also get sum of forces in the normal direction. So the same kind of stuff. So this would normally be x and y, but in this problem, we're using normal tangential because it is a rotation problem. That is mass acceleration of the center of gravity in the normal direction. Again, we don't normally want to use that, so we can sub that out. So the standard one that we use is v squared over rho. V squared over rho. Now don't confuse this rho for density. This rho is our radius of curvature. This is, if we recall, this v can be rewritten as rg omega. So if I sub that into this problem and assume that rho is equal to r, which it should be in these problems, because as long as this distance from here to here is fixed, doesn't change, then it will be. Then I get the following equation, which is a lot nicer. Mass times rg omega squared. So this one uses our omega, this one uses our alpha, which is generally what we want. We'll know generally the mass and the radius, so it's a little more useful. Then we get our new equation for moments. So the default one is sum of moments about the center of gravity. I'll assume right-hand rule positive, equal to the mass moment of inertia about the center of gravity times alpha. Now, it may not be convenient to find the sum of moments about the center of gravity. Instead, we may want to find sum of moments. So in this problem, it's actually more convenient to find the sum of moments about point O. So that is actually an instantaneous center. So any instantaneous center, we can do it as I about the instantaneous center alpha. So we get a choice. We get to use 3 of these 4 equations whenever we solve these kind of problems. So for this problem, well, we don't want to start off with forces in the tangential direction because we don't know alpha, and we aren't going to know all of our forces. We're gonna have the normal force in the tangential direction and alpha, so we'll have 2 unknowns. This probably we can't solve it instantly. Forces normal, we could do that one. We know the mass, we know the radius, we're given omega, so we could do this one instantly. The only things we're going to have in the normal direction are going to be gravity, which we know, the weight, which we know, this pulling force, which we know, and On. So we could do that one right out of the gate. And then we can also do one of our moment equations. So I'm going to start off with forces in the normal. Sum of forces in the normal direction. So again, we're going to use this nicer form down here. You don't always have to use that, depending on what you need to find. Mass, radius, g, omega squared. So because omega is squared, we don't care if this is positive or negative. So there's sum of forces, so I'm going to assume up is positive, so just following our normal direction. So we're going to have the reaction force O of n. We're going to have the 3/5 component of P. We're going to have gravity going down. And then we are going to have, on the right-hand side, our mass. So our mass was 30. The radius, so the distance between the center of gravity and this. So this wheel, forgot to write that in. This wheel has a radius of 0.3 meters. So it is 0.3, because this is one radius here. So 0.3. Now, you might say, oh, well, the distance is negative 0.3 because from O to the center of gravity is negative. But what we actually want to do is this is a lot like when we do 2D moments. We want to leave all of these numbers positive, absolute value, and then we're going to manually determine the sense of the acceleration. So remember where this comes from. This comes from the acceleration of the normal. So we want to figure out if that sense, the produced acceleration, is going to be up or down. And if we start throwing in all these extra signs, sometimes we'll get that wrong. Our omega is 10 squared. And so then we ask ourselves, if this thing is rotating as it's showing, so it's going to kick over this way, will our acceleration be up or down? So if you visualize it, kind of say like 1 second later, we expect this dot to be up. So we expect that it's kind of accelerating upward. So we will leave that as a positive number. So we're going to have to determine the sense manually. That might be a little bit weird. So yeah, don't throw in negative signs on this side. Just manually determine what it should be. So the mass should be positive all the time, and then for everything else. So you solve this, you'll find that On is 1,164.3 newtons, which should match the answer. All right. So next, let's go find, so we can't do forces tangential yet because we have too many unknowns in that. We could write it out, but we would just be writing it. So next, we get to do one of our moment equations. We could technically do both of the moment equations and never do forces. So again, you can choose any 3 of these. So I'm going to do moments about instantaneous center, because if I do that about O, then OT won't show up in our equation, and only alpha will. Whereas if I do it about G, then I'll have a moment produced by OT and alpha, and I'll be in the same boat as I am with this problem. So sum of moments about the instantaneous center, I'm going to assume right-hand rule positive, equal to I about the instantaneous center, alpha. So we're looking for alpha here. So our moments are going to be created. So this is in line. So here, the force G is in line with O. ON and OT are at O. So the only things that produce a moment is this force P. And we're going to have the vertical component and the horizontal component both producing a moment. So the 3/5 component will act 0.3 meters away. It'll produce a positive moment. The 4/5 component will act also 0.3 meters away, and it will create a positive moment. This will be equal to I instantaneous center. So to figure out what that is, we need to go back to our book and look at our disk. So for our disk, we need the mass moment of inertia about the instantaneous center, so Z prime. So that's going to be 3/2 mr squared. All right, so I've written that down. So 3/2 mr squared alpha. So the mass of our wheel is 30. So let's just clean this up. So we'll have 30 times 0.3 plus 40 times 0.3 equal to 3/2. The mass of this is 30. The radius is 0.3 squared. And alpha. So alpha will be the only thing left in here. You solve for alpha. Alpha will become a positive 5.185 radians per second squared. And so that means that it is counterclockwise, as we guessed. All right. And then to finish up, we now get to use sum of forces in the tangential or sum of moments about G. I'm going to do forces because they're generally easier. So sum of forces in the tangential direction equal to mass radius G alpha. So again, we now know alpha. So that alpha is going to be that 5.185, and we do put it in as a positive number. The radius we know is a 0.3. So this is the same thing. So for this set of numbers here, 0.3 times 5.185, we're trying to determine the sense manually. So just put these in as positive numbers. So even if this was negative, we would put this in as positive. And then we come in here and we ask ourselves, is the acceleration to the right or the left? We expect, based on what we know about omega, the acceleration is to the right. So therefore, we want to make sure that the sense of these two numbers multiplied together is positive. So they are, but, so there's that. And the mass is 30. And then the forces in the tangential direction, sorry, I'm jumping back and forth, is tangential, the 4/5 component, and that'll be it. So we have O tangential plus the 4/5 component of P, and that'll be equal to 30 times 0.3 times 5.185. And like I said, we determined the sense of this to be positive manually. The only thing left unfound here is OT. So OT will become 6.665 newtons. All right. So let's see, I can't get all the answers on the page. So if you have any questions, feel free to contact me.